So it's yeah, I guess I knew Igor much less than many of the previous speakers. So we came more or less from different areas, but I intersected several times with him, and it was very nice to discuss mathematics, especially being from nice different areas. You would find some intersections, and I had two projects which would have benefited if he was still alive, but somehow we didn't finish discussing before he went. And he also was a very, very nice person. And part of what I'll be trying to tell, it sort of relates to this thing which was already thrice repeated today, that Igor liked very much beauty in mathematics, and he thought that if there is a possibility for beautiful solution in some problem, it should be there. Well, I sort of maybe believe less in it, so often I can't find that beautiful solution. But I will try to talk about one such case, and it's sort of some very old results, not by me, some old results by me and a bunch of my students, and some newer ones. So those who know, for them, it's a kind of find what is new in this talk. And yeah, for Andrei, it's what is the one thing which changed since February. It's, well, so there is, sorry? What changed? Month changed since February. Well, okay, today is 2nd of the 7th, and that was 7th of the 2nd, so not, not very much. So there is, it's based on some of the joint work with Clément Angler, Ansi Kemppainen, Misha Christoforov, and also Sasha Glasman and Dima Chelkak. But the whole story sort of starts with us trying to understand the famous paper of Belavin, Polyakov and Zamolodchikov, which would be 40 years old today. So this is this famous paper, which is called infinite dimensional Zamolodchikov. So infinite dimensional conformal symmetry, or just infinite conformal symmetry in two-dimensional quantum field theories. So that's 40 years ago to the date. And I come from complex analysis, so it's a different area. And of course, that you have some, well, as a complex analyst, I can come up with infinite number of objects which have infinite conformal symmetry. That's what we do in complex analysis. So that part is not very exciting. What is exciting is that they came up with natural objects from other areas which suddenly exhibit infinite dimensional conformal symmetry. So what we mean here is that if we have a 2D field theory at criticality, then what was known before, there is this work which dates back to Stuckelberg and then Wilson, Kardanov, and Michael Fisher, that we have a randomization group theory. So the field theories at criticalities, they're kind of fixed points of this randomization. So we expect them then, but in most cases we can't prove this mathematically, but we expect them to be invariant under rotations and translations, because if it's not invariant under rotation or rescaling or translation, then, well, you just rotate it and then there's another fixed point. Okay. And then there was this leap of faith made by Polyakov. So first he said that, well, let's also suppose that in 2D they would be invariant under inversion. Well, a priori there is no reason to do that. Like if you take Brownian motion in 3D, it's not invariant under inversion like 2D. And I had to discover it 3 times, and always I was very much surprised what's the difference between numbers 2 and 3. And then he suggests that it's invariant under all conformal maps. There is if you are a complex analyst, if you read this paper, there are very sort of dangerous things, because they say, well, okay, there are infinite dimensional semi-group of conformal maps of domains to domains, and then we just apply this group to the whole plane. And then it's sort of, well, okay, you're allowed to do it if you are a genius in physics and you get the correct results. You're not allowed to do it if you work in math department. The thing is that actually, yeah, maybe I should also write the name Cardi, because he was the first to work out how to do the boundary properly in the same year, 1984. But Cardi also has a counterexample with Valentina Rio, where you have a field theory in 2D, which is sort of rotation, rescaling, and translation invariant, but doesn't lead to a conformal field theory, and it's something logical and physical which comes from the elasticity theory. Now, what is the sort of specific application which kind of puzzles complex analysts or a probabilist? So doing this, I became a probabilist a little bit. Is that if you take a sort of some lattice model of statistical physics, so one shouldn't say lattice model, one should say lattice model of something, lattice model of, well, of something, of some phenomenon. So at criticality, we assume that when the mesh of the lattice goes to 0, goes to something conformally invariant, so conformal field theory. And this is sort of a very surprising thing. So the question is, why should this be? There is a counterexample by Cardi, and how to prove? Because basically up to that paper, or rigorously up to recently, there was an example due to Paul Levy, which says that, well, it's Paul Levy and Pola and a bunch of other people that, and Wiener, that random walk converges to Brownian motion, and Brownian motion is conformally invariant in 2D up to time change. So there was this example, but basically the question is, so how you would prove this thing? But before I would say want to say a few words about what do I mean by lattice model with criticality. So I have pre-drawn a couple of lattices because square lattice is very easy to draw, but hexagonal is much more difficult. And I will just mention two sort of or three canonical models which encompass like a dozen most classical models in statistical physics. So the one is a sort of loop representation of O of n model. So basically, O of n model is generalization of Ising model where instead of plus minus spins, you take vectors on an n-dimensional sphere. So for example, XY model of Heisenberg, which he invented because he read thesis of Ising, and Ising in his thesis conjectured that there is no phase transition in Ising model. So he decided to come up with a new model, and that's called now XY model. So they both fall into this case. And there is a loop representation where you basically draw the loops on the hexagonal lattice, and you write partition function as a sum of all configurations of n to the power number of loops. Well, that's the same n as here. And x to the power length of loops. So you can get, for example, from Ising model to this model in two different ways. You can start with Ising model where spins are on hexagons and then draw the domain walks. And then what n will be equal to 1 in Ising model, you don't count the number of clusters, and x will play the role of temperature. So actually temperature will be the reciprocal of minus logarithm of x. But it includes, but there is another way that you can do spins on the vertices of hexagonal lattice, and then you do high temperature expansion. So these sort of loops, they don't separate classes, but they kind of run within the classes. And there are lots of combinatorial bijections in this area. It's actually fascinating how much fun combinatorics people have done already, and probably still can come up with a new bijection. I haven't mentioned whatever bijection I discovered. Turns out that someone had it already in 1961 in some obscure paper. So here there are several sort of famous cases for that. So if you take, as I said, if you take n equal 1, you don't count the loops, then you have the Ising model, and the critical x will be 1 over square root of 3. It's a paper of Vanier, which follows Kramers and Vanier, who did it for square lattice. And then you get percolation for x, another critical value equal to 1. And then if you take n equals 0, you get self-avoiding polymers or self-avoiding walk. So what happens if n equals 0? There is 0 to the power number loops, so we don't count loops at all. So there is nothing, so to say. But you can enforce boundary conditions that there is a source and a sink, so there is a curve running between them. Well, if you put small x you would minimize the length of the curve, so you get a straight line. If you put large x, you have a space-filling curve. But there is, again, two critical values of x, and the most interesting one is xc 1 over square root of 2 plus square root of 2. Well, let's just add that for n equal 2, you will get this xy Heisenberg model, and there the critical value is 1 over square root of 2. Okay, so there is actually a formula in terms of n. Now, the interesting thing that if you take the original of n model, n is the dimension of a sphere where your spin lives, so n has to be integer, but with this reformulation, so it works as a bijection for 1 or 2 or 0, but you also can now put any value of n, not necessarily integer. Okay, so this is the model, the problem with this model, well, besides the fact that we cannot do it for, we can do it only for a few parameters, so we can do this and that. So this I did with Dimitrov, and this I did myself, and this we can prove that this is a critical number indeed, but we can prove that it's conformally invariant. So the problem is that it's not so easy that, for example, for let's look n not equal 1. If I cover part of this model and you see this sort of two yellow things, is it a part of one cycle or different cycles? Well, in this case, it's easy because they come to one vertex. But normally, if you cover half of the model and you see 5 half loops, it's not clear how much they really contribute to the weight. It may be part of the same loop going on in and out or different wise. So there is this sort of non-locality, which is a big problem, what to do with it. And the other model I would just say, because what I'm going to say, it works very well in 3 different setups, is what is called Fortuyn-Castellan model or random cluster model. Well, there is this joke that if you do like statistical physics, you name models after your students. So, for example, Lenz invented Ising model and named after Ising his student, and Domp invented Potts model and named after Potts his student, and Castellan invented FK model, but he decided to add his name nevertheless. So this model is basically the same thing, only you do dense loops on square lattice. So the partition function is usually the right square root of q, so let's say n is equal to square root of q. So it's sum over n to the power number of loops. So you don't have x here because you have dense loops, so the perimeter is always the same. And it's related to some random cluster model on this lattice, which is at 45 degrees. So it's or to the dual model on the dual lattice. So for example, if you take n equal 1, you will get percolation, because n equal 1, you just have the same probability for loop collections, and it would be just the same probability for sort of bond collections on this 45 degrees lattice. Sorry, no x, because it's a dense collection of loops, so it's always the same perimeter. So it's in the original model, you start with the random cluster model. Again, I would say that it's a loop FK model. So in the random cluster model, there is x, but it disappears when you do bijection, because basically x would cluster how many would count how many clusters you would have, and for critical one, you do when you do loops, it counts loops 1 to the power number of loops. So there is some combinatorial miracle. So n equals square root of 2. It's again some version of Ising model. It's a cluster representation of Ising, and for n equals 0, it's a uniform spanning tree. So again, we can do FK Ising, so and we can do UST, that was Lowler, Sham, and Werner, and Rick Kenyon before them. Okay, so the question is what to do with this non-locality. And then there is this trick which was invented by Baxter. So it's in no relation to the his Young-Baxter equations. Is that what we do? We orient the loops. So instead of looking at unoriented loops, we randomly orient them. So we look at the picture like that. So for example, here one is clockwise, one is counterclockwise. And then, of course, if I orient them, I should write new partition function. And the tempting thing is of course, to write n over 2 for clockwise, n over 2 for counterclockwise. But what I do, I take a vector mu, which is a unitary vector, so that twice mu is n plus im, and it lies on a unit circle. So it's in particular, if mu belongs to the unit circle, mu absolute value of mu is equal to 1, and well, mu bar is mu inverse. And now what we do here, we write the partition function, the complex partition function, to be sum of mu to the power number of oriented loops. Now this loop is counted as plus loop, and this is a minus loop. So for example, in this picture, it's number of oriented loops is 0 because there is one plus loop and one minus. So this has weight mu, this has weight mu bar, this has weight mu. So x to the power length. And then you can ask a question why this is a local weight. So what you can do this, let me maybe write it in red, that what you can write is the sum of the lambda to the power number of turns, well, x to the power length. So basically what you do in the left picture, you say that whenever you have a left turn, you put to it the weight lambda. When you have a right turn, you put weight lambda bar. And then what happens if I go around the cycle? The total turn of cycle is 360 degrees. So in 60 degrees turns, it's either 6 or minus 6, because left and right turns, they cancel out lambda and lambda bar. So if I choose that lambda to the power 6 is equal to mu, so then this is the same weight. But this weight, it just locally counts how many left turns I have, how many right turns, so I cover half of the picture, I see everything. And the same you can do on the right. So the only difference on the right is that you have now the, well, let's say, let's draw it in yellow, the left turn and the right turn, the lambda and lambda bar, and lambda to the power 4 is equal to mu. And then you have this, let's say, complex loop model. So the Z complex is equal to sum of mu to the power number of oriented loops. Now, what we gained? We have now a partition function which is locally defined, so it's sort of much nicer. But it can't happen that you gain something and you don't lose anything. So of course we lose something. What we lose is that instead of a probability measure, so we had a positive partition function here. If you normalize by it, we have a probability measure. Now we have a complex partition function. Still, it's when we forget the orientation, we project to this. So the total mass of this complex measure is the same. But its variation is very, very big. So the bigger is the volume, the bigger its variation. It grows exponentially. So you have a measure of infinite total variation, but total mass 1. There are lots of cancellations, so it's hard to do estimates. And then there are other funny things which don't work. So for example, so the bad things is that expectation of f bar is no longer equal to expectation of f bar, which normally is true for, or integral with respect to this measure of f bar is not equal to the bar of the integral, because measure is complex. So you also, if you want to write this thing, then you would need to write here expectation with respect to measure mu bar, and then it's kind of more difficult. And then it's, if you start writing this, you make this mistake like every week for the first year, so it's a bit problem. Now, in this case, in this particular case on the right, there is another projection where you forget the loop, but you leave the arrows. So let's forget how the loops are connected, and we leave the arrows. We get this picture. And let's look what happens with this picture. So there are apparently 8 different ways how our loops connect at a point. So one way, which is repeated 4 times, is that they are connected like that. And this is, there are 4 ways to do it in southwest, southeast, northwest, northeast directions. So what is the weight of this picture? There is one left turn, one right turn, lambda, lambda bar, they cancel out. So lambda times lambda bar is equal to 1. So weight, for example, the weight of this vertex is 1, because there is one right turn, one left, and there is no other way to split it into turns. But then there are also twice the things which you have, for example, turns like that. You come sideways and you go vertically. And when you forget the turns, it's the same picture as this one. And while the left picture is 2 left turns, so it's lambda squared weight, the right is 2 right turns lambda bar squared. So while they both have complex weights, the total weight is lambda squared plus lambda bar squared is actually real, because lambda is a unitary number. So it's a real weight for this picture. So usually it's denoted by C, and this is usually denoted by A and B. So this is the so-called 6-vertex model. So in the particular square lattice case, there is a projection so that again all weights are real. And again you have probability measure. But then there should be a catch, because we should lose something. What we lose is that boundary values you would like to have here, they are not the same as boundary values you would like to have there. So actually, if you notice in this model, everything is real inside, but the boundary values here, this is a left turn, so it's a complex boundary value. So it's a bit problematic, and that's why people had problems with this thing up to now. So I would want actually, so as I said, I had big problems with this, but there is an interesting earlier piece of work which indirectly had conformal field theory. So this is work by first it started with 2 Dutch scientists, Nienhuis and Nijs. So it's 1982 plus. So it's basically called Coulomb gas. Yeah, maybe I will leave more space. I will just write it here, Coulomb gas. And their reasoning, so they started with this picture, but then they also did this picture. So they start with this reasoning. Suppose we have this model, and we did this bijection, and we have this picture, which is set of lines, and it's a real measure. Now, when we have these arrows on the lines, you can view it as a geographical map. You know, like in geographical map, around the hue, you have these Lebesgue curves at every 10 meters or every 100 meters. And to know whether this is a hue or a hole, you need to orient them. So if they're oriented counterclockwise, you're climbing Mount Everest. If you're in Mariana Trench, they counterclockwise. So basically, this orientation gives us a height function. So this is another good thing. So the good thing is the height function, let's say h. Well, h capital maybe. H. So, for example, here it would be like you start with the height function 0, 0, 0, and here it would be 1, 1, 0, and here you cross differently minus 1. So height function h, basically you go from 0 to 1 or from 0 to minus 1 when you cross in one direction or another direction. Well, you can make a few, well, again, whatever I say up to now, it's not proof. Those are ingenious physics arguments. By the way, smart people who take leap of faith and then they land on hard ground. So they said, well, okay, we believe in Wilson, Kadanov, Stuckelberg, and Fisher. So by linearization theory, there should be some scaling limit when we tend the mesh of the lattice to 0. So we have a random height function with some measure on it. And even the measure is real, so there should be a limit. Let's try to describe this limit. So basically, they say that we take h with the mesh of the lattice, and it converges when mesh goes to 0 to some function h, so it's a random height function. And then we try to write partition function for this h. So basically, what we get is some sort of exponential of minus, well, let's say integral over all blah, 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 blah configurations. And then, look, our weights in this model, if you look, the weights were different whether you have this connection or this connection. So this connection corresponds to a saddle, and this connection corresponds to a slope. So the weights only depend on the gradient of height function. If you have a saddle, the weight is 1. If you have a slope, the weight is c. So there should be some weights which only correspond to one gradient of height function. Obviously we believe that everything will be rotationally invariant because we believe in a randomization group. It's clear that it's rotational with respect to 90 degrees, but again, it's a sloppy thing. If you do like diffusion limited aggregation, then you still see the lattice structure, though it's as physical model as this one. But it's rotationally invariant, so it's everything function of this and other terms and so on with some coefficients. But this coefficient we denote by let's say g over 4 pi, yeah, I remember once when we had birthday of Ludwig in Geneva, Ed Witten asked Nikita a question, and what is this pi in that formula? And then Nikita went like that and looked at this. This one is the circumference of unit circle. So it's the pi which is circumference of unit circle. No, well, it was wonderful. I will come later to why there is pi here. But then I have an argument that you shouldn't have any of these terms. And of course, the argument is that you should first check the simplest possible thing. But the other argument that if you actually compare 4 points nearby, you can get the bar or Laplacian if you really try really hard, but you can get higher order operators. So they sort of make sense. And then, what happens is that this parameter actually changes things, because what we have here that when you rescale, it's not a scale-free model, because we already say that with one lattice step we jump plus minus 1. Well, they actually plus minus pi in their paper, so they have slightly different normalization. So it's different, should be different g. And what's miraculous in their paper is that they write this formula, they make this ansatz, and this is the object which is called the Gaussian Free Field or free boson in physics literature. And this object, which is conformally invariant, very well studied, is a two-dimensional analog of Brownian graph on a line. Unfortunately, it's a random distribution, and you know we have like exponents of random distributions that in math we usually don't do. Basically, this boils down proper problem of like calculating dimension of clusters or critical exponent boils down to some calculations with this guy. These mathematicians know fairly well how to do. And the only question is determining g. So basically, you calculate one thing you already know from other methods, you determine g, and then you can calculate other things. And that came before BPZ. By the way, I must say that conformal field theory, I'm really looking at the first corner of conformal field theory where the simplest theories are. And the reason why I'm more excited, because I'm simple complex analyst. Well, I'm complex analyst. So I like very much this relation with nice discrete things. And here, of course, you can pose the very same questions, why and how. So in particular, in their papers, they always deal with cylinders or tori. And the reason they do that these complex boundary conditions are not easy to tackle. So that's, and I spent actually with John Carty, we spent twice 1 week trying to do it and could not do it. And I will try to explain today how to do it. So we were smarter back then than we were before, hopefully, or wiser, I don't know. And what I would say, it works also on any Riemann surface. Okay, so yes. Yeah, of course. Look, the point is that if you have a torus, the point is only periods around two homology classes. Yes, the periodic disappears. But for example, they couldn't. They did cylinder and they did torus. But for example, they couldn't do plane because it was not clear how to do large volume limit. Actually, Gaussian free field in the plane is an unclear subject. And in bounded domain, it's also an unclear subject. So we will come to that later. Sorry? It's an interesting thing. So, for example, they apply the same logic here where there is a complex measure. And they say, well, it's a complex valued field, but in the limit it's real valued. So it takes values in the real line, but then it turns out that even if you do this properly, the imaginary part pops up. No, you can't reabsorb it because you change then it's plus 1 over 1 lattice step. It's a relation of 1 where you move in this sort of height space to the lattice step. You can't reabsorb it. No. It's a bit counterintuitive. It's not what we are taught about Brownian motion or Gaussian free field, but the reason is that there is a scale built in, and it's sort of it remains when you pass to the limit. So it's okay. So let's try to. So where do we go next? And how much time do I have? Okay, I have this problem that if I give the same talk second or third time, each time I speak longer because I have more jokes to crank. Okay. So let's just ask the question. So how to get conformal? So how to put conformal in conformal field theory? Suppose we want to show that some discrete object has a conformally invariant limit. How to do it? Okay. So I've been doing complex analysis for living for a while, and well, not anymore, but I've been doing it for a while. So I probably know everything about conformal invariance, and there are like, well, I don't know, 20 like extremal lengths, harmonic phi, extremal harmonic phi, many. Most of them, they can be discretized, but the problem that most of them, they are defined by some global thing, and it's difficult to check that certain thing built on the model has global properties. So the easiest probably, yes. That's the interesting thing. So this C is not central charge. This C is 6 vertex model constant. But the region about which we are interested, so for example, in both these models, so the central charge C, which is not that C, it goes from -2 to 1. So -2 is uniform spanning tree. It was, let me show you uniform spanning tree. Here's uniform spanning tree. And 1 is like double dimer model, or this model for, well, xy is 1. And Ising is 1/2. Now you ask a question. Yes. Yeah. So the central charge is related to G. If you want, let me just check. As Peter Lux once said, never differentiate in public. So it's, let me just try that G is equal to 1 plus E0 over pi, or equal to 4 over kappa, or equal, wait a second, I didn't write for C, okay. But it's from this you can deduce. So it's quadratic relation to C. It's also quadratic relation to that C. The two C coincidentally are different. But, this is one of the questions. Why on earth, why C to JFF, a map to JFF? That's not how it's supposed to be. And it's, okay, so usually people would say that there are screening charges, and actually people who were doing donuts and canionis, they were saying that, okay, if you play this game on a donut and you have a loop which goes around the donut, its total rotation is not 360 degrees by 0, so its weight is 1 and not mu. And so this is like the screening charge which changes the central charge. No, it's not. Okay, so it's, well, it kind of contributes that, but it's not, yeah. So it's, but yes, I agree. So I searched for the answer for 15 years. Now I think I will try to communicate it in the remaining 25 minutes. Yes, yeah, you see it everywhere. You see it in simply connected geometry. You see it. It's actually fun. It's really fun. Yeah. So it's well, the question is whether I can prove it or whether I should move to physics department. It's a different and more complicated question. Yeah. So it's so basically what I want to do is that just to say how to get conformal. So the easiest conformal invariance is that, say, holomorphic or harmonic function with given boundary values. So basically, the problem we all learn is that Dirichlet problem for Laplacian. So Dirichlet problem for Laplacian is conformally invariant. So we learn that in 2D, you just map your domain to a disk or a half plane, whatever your favorite domain is. There is an exact formula for Poisson kernel. You solve it and you map it back. The same goes for D bar. There it's only you can prescribe all the values, but you can prescribe real part, or you can do some other funny things. The nice thing is about it, it's easy to discretize. So easy to discretize, especially for harmonic functions. So that's basically function is harmonic if on a graph its value at every point is the average of the neighboring values. And we have seen harmonic functions on the line in a, well, massive harmonic functions on the line earlier talk of. Actually, yeah, we have seen it many times already today. So this is easy to discretize, but unfortunately not canonical. So the thing is that, for example, if you do harmonic function, you can say that it's average of all first order neighbors or average of all second order neighbors. Those are different definitions, different space of functions, but in the limit, both Laplacians will converge to the same Laplacians we denote by letter delta. Well, some people denote functions by letter delta, but earlier today, but I denote Laplacian. And it's kind of universality that if you take a limit of a random walk, any random walk, it will basically in a plane, it will converge to Brownian motion with a drift. So there are only basically 4 parameters. There is the speed, well, there is sort of a matrix of correlations and speeds, so there is this sort of strong universality. And on a line, it's just the speed and whether there is a drift. Okay. 2D. I'm discussing only 2D. Well, when I publish this, I will move to do 3D. Okay. Yes. Yes. Sorry, wait a second. So, what's the question? Yes. Yes, but it's a topic of separate lecture. Actually, UST, it's an interesting thing for 3D. So UST is related to harmonic function, and Kirchhoff knew this in 1847, and it's related to harmonic functions in any dimension. And it's a question why we cannot analyze as nicely as we can analyze using module in 2D. Why can't we analyze as thoroughly QFT corresponding to UST in 3D? So that's well, a subject for an interesting discussion. So I would actually make maybe here 2 remarks. So one remark is that basically Cauchy-Riemann equations, the usual way we write them is that there is a complex derivative, but or if you have a boring calculus course, they write that ux is minus vy and uy is vx. I might have with probability 1/2 I got the signs wrong, this is sort of equivalent to writing that you have a flow which is divergence free and curl free. And this is sort of, we have seen yesterday the Durand forms. It's like one forms in 2D. Delta and delta star are basically the same. They map to 0 and 2 forms, and these are 2 operators. So this is why 2D is so special with analytic functions. But you can do it differently. So for example, the way we did it here for the Ising model, we just summed the values of function at these 4 points with coefficients 1, I, minus 1, minus I. And this was basically the first of the 2 operators, because if you check carefully, if you have function defined on edges and one relation per vertex, then you have twice more unknowns than relations. So it's actually only this thing. Well, it depends how you look at it. And then we're getting the second one, which was 1, 1, minus 1, minus 1. And then this was somehow this setup is very nicely adapted to Ising model because you get square root of dz form, fermions, and all that, and it now pop up in random surfaces and dimers also. But morally, if we find something which has this property, we would think that it is holomorphic. It's just if we believe in renormalization group and we think that there is a limit of whatever we found, then just having this relation is enough to believe that it is holomorphic. It's not enough to prove it. And maybe let me just say that one more thing that boundary value problems. So there is another important thing is that the covariance, it's equivalent to the boundary value problems. So you can write, I made an example of invariant object. So it's if you say that m of z is equal to n of phi of z, so you have two domains and you have a map phi, and you have here some field or some observable, like margin of some field, and m is mapped to n, and you ask how they are related. So for Dirichlet problem, it's just this relation. If you preserve the boundary values and you map, and basically this follows, you can say that your objects are invariant, and then you map everything to a nice model, let's say to a disk. Let's draw a disk, and or you can say that the boundary values are the same here, and it will imply invariance. So this is the same. But there are more things. So for example, you can do this thing. You can just take f prime z to the power sigma, and then my small contribution to Ising model into D was to observe that the Kaufman or Kadanov-Cherev fermion is actually an analytic function. So it's actually an analytic function which changes by the rule with sigma equal to 1/2. So it's a square root of dz form because they were writing basically relations like that without realizing that it's an analytic function. And that corresponds to boundary values. So boundary values also should change like that. And on the boundary, phi prime is basically dz. So this corresponds to the boundary values is that of the type that m is collinear with square root of dz. So this is, well, square root of dz to the power sigma. But then there are more covariances, and maybe I'll just write a few of them. So it's you can write m of n of phi of z plus some parameter alpha log phi prime of z. So you can have an invariant thing, but which is a little bit with a complex twist. So you see that this, if you have real boundary value, it always remains real. But this you can start with disk and real boundary value, but whenever you map, you add some complex thing. So you start playing with real Gaussian free field, but oops, you are required to add complex things. Then you can differentiate that. So this is something for fields like GFF. And you can get n of phi of z times phi prime of z. And let me put a different number better. So now you have phi prime of z logarithmic derivative. And this is basically metric element and things like that. So for example, if you want to play with GFF, this would be the thing for the gradient of GFF. And then there is one more. So this is what in complex analysis people call pre-Schwarzen, pre-Schwarzen, and Schwarzen. So this is for quadratic differentials, phi prime of z squared plus gamma Schwarzen of phi. And Schwarzen of phi, again, I always write it wrong. Schwarzen of phi of z is, what is it, 1/2 phi prime over phi prime minus 3/2 phi prime over phi prime squared. And this basically all of it, is it 1/2 or is it? No, it's just like that. Yeah, sorry. Yeah, that's. So this is an interesting thing that it's an interesting exercise that those are basically the only thing which satisfy chain rules. Because if you want to write something like that, you should be able to apply another psi. And when you start writing chain rules, other things start popping up. But here, it's the only way they cancel out. So this is kind of a taste of what is about to come. And so let's just write. So what we were able to do before, we were able to write some observables for the Ising model and self-avoiding walk and percolation, and they were basically observables in this class, so they had different spins. So for Ising, obviously 1/2. For percolation 0, logarithmic quantum field theory. So I will write one for 6-vertex model, and then there is sort of a miraculous thing that you do the same parameters here and here, but you get, and you do the same observe, but you get different values. And the reason is that here there are like these complex things for turns, so you part of your spin you kind of sweep under the carpet into these things. So basically the thing I want to write is, so let me just say, yeah, so this is like the new, well, new stuff. So, so what we do, we write, again, so we do 6-vertex model. So we have this parameter C, which is square root of mu plus square root of mu bar, or equivalently, what was that? Lambda was my parameter, yeah. Lambda squared plus lambda bar squared. So what we do, we start with some model, with our 6-vertex model with some boundary conditions. And then we assume that we have a no, it's ABC. You know, it's the weight, it's ABC. So my in physics department, is my situation is A equal 1, and C is equal to this. Delta is A squared plus B squared minus C squared. Well, Pythagoras theorem, sort of, yeah. No, we, you know, I have to move to physics department because I'm not giving proof. Yeah, so it's, well, I'm sort of giving proof. So suppose that we have what we introduce a disorder operator. So we say that there is an edge in our 6-vertex model where there is a hole in the floor, and this sort of plumbing is wrong and everything is going down there. And then we introduce 2 sources on the boundary. So it's 2 half sources which pump 1 gallon per minute from the boundary, and 1 double sink which sort of sucks 2 gallons of water. And then we try to see whether it satisfies Cauchy-Riemann relation. Just partition function of this. So we write that basically, well, let's say f of z, where z is this point, is the partition function of what I've written, of this plus operator, minus operator, sorry. But then we also introduce the weight nu, and we put nu to the power winding of these yellow curves. So it's so winding of these yellow curves. So for example, in this case, they make 2 left turns. So it's like the lambda, but lambda is for all curves, but for yellow curves we add nu. And the reason why we do it, because these curves are sort of special, because this is how water flows into this sink. These curves are easy to control when we move this point around, if we want to check Cauchy-Riemann. And it's actually uniquely defined, because for any picture, you can uniquely trace this curve. You cannot uniquely trace, they might go like that, for example. But however you trace, they will still have the same winding. It's an exercise. So it's sort of, well, exercise well-defined. And then what you can do, you can draw sort of possible pictures in the neighborhood of some point. So you can have picture, for example, like this. So suppose that this is some point, and we can have picture like that. But then we can move this point up, or we can move it down. So we can make also the picture like this. And we can also make the picture, let me see, like that. And our plus operator, or minus operator rather, it moved from here to up and to down. If we want Cauchy-Riemann equation, then we have to sum it with weights, let's say, what is it would be? Minus 1, I, and 1. And then the weight of the whole picture doesn't change except for weight at this point. And the weight at this point, it was 1, let's say here, because the curves go like that. It was C here, because the curves go like this. The second possibility, it's 1 again. And then the number of lambdas, number of mu's change also, because, for example, when we go up here, on this picture we had no turns so whatsoever, but on this picture we have one left turn and another left turn. So we also get mu squared, and here we get nu to the power 4. So basically the question of Cauchy-Riemann, so the Cauchy-Riemann question is whether we can find the value of nu so that this thing is 0. And the easy lemma is that yes, we can. So the easy lemma, so it's sorry? Look, 6 vertex model is always critical on this line. We choose it with such parameters, it's always critical. It's actually always critical. And we're automatically in the chaotic regime, not in ferroelectric. But lemma, basically, you can rewrite this thing. So I would just factor it out. So if you remind that C is square root of mu plus square root of mu bar, then this equation, it factors out as mu squared plus I square root of mu times mu squared plus I square root of mu bar is equal to 0. So basically, this is the recipe. So it's basically, you should, one of these is not interesting, so this one is interesting. So this one is trivial, you just get it from sliding up and around. So basically, when mu square is equal to minus I square root of mu, you get homomorphicity of this observable. Now, as always, it's like remaining 9 minutes, I do the interesting stuff. So the interesting stuff is that you can do it slightly differently. So it's an observation that basically what you can do if you, for example, take this picture and then you take this picture. So the weights of these two pictures, here it's weight, the weight 1. Here the weight is nu, so this made 4 left turns, and this made 4 left turns, nu to the power 8. But let's compare the height function. So here the h is equal to 0, here h is equal to 0, and when you move, you cross 1, it's equal to 1, it's equal to 2. So basically, instead of putting this weight, you can put the weight rho to the power h of z, rho to the power h of z, and you should just check that rho squared is equal to nu to the power 8. So of course it's slightly more complicated because you should also check it for things which are rotated 90 degrees, because then, so it's actually, strictly speaking, the lemma is that f of z can be written as the sum of all configurations plus operator times rho to the power height function of z times some c of the type of the z. So z, you cover lattice in 4 covers depending on the direction of the h, and then c will be slightly different. Sometimes it's 1, sometimes square root of r, but well, so c is either 1 over square root of rho. Okay. Now, what's the bonus thing of this approach? So the first thing is that we can do any boundary conditions. Because here I appealed to this picture that there are 2 sources and that there is a unique connection. Here I just can do local reconstructions, nothing bad. Then, of course, it should come at some, so also we can do plus operators times rho to the power h, or we can do minus operators times rho to the power minus h. Because, well, no, it was minus operator here. Yeah, it was minus operator. So if I change from minus to plus, it means that I have to change the directions of my curve. So I change from minus to 2. So it's basically these 2 things. Now, what is the trick? The trick is that this thing that h of z is defined up to monodromy. Because if I have for example, my thing, and I have, for example, plus operator and minus operator, then what happens when I walk around minus operator? There are two curves which end up in minus operator. So when I walk around the minus operator, my height changes by +2. So my height in this domain is not well defined. You can have a geographic map where there are two level lines which collide. It's kind of a pole which is put in the ground so that if I walk around it, that I'm 2 meters higher, taller. Not 2 meters tall, but 2 meters higher elevation. On the other hand, here, it's -2 height function. So basically, because it goes in the opposite direction. So basically, to make it legal, there is one easy way that you do crosscuts. So that's what you usually do when you study Riemann surfaces. You make crosscuts. And then when you think of it, you can define this function independently of crosscuts, so you can move them later. But if you want to do calculations, you can fix crosscuts, but you should be mindful that when you cross around them, then the height function changes. But this is a good thing, because I love monodromies, and every complex analyst loves monodromies, and many of those complex analysts were mentioned in the previous two talks. So it's who love monodromies. So what does this thing mean? Let me do two things. So first, suppose we have plus operator, and suppose we rotate it 360 degrees. Then what will happen is that it will get entangled in its own crosscut when you rotate it. So it will cross its own crosscut, so the h will change. So what will happen is that when you rotate it 360 degrees, you multiply by rho squared. When you multiply minus by 360 degrees, you also multiply by rho squared. Why? Because you cross the line which goes in opposite direction, so height does not decrease, it increases. But your weight is also minus height and not height. So it's the same multiplication. And then the fun stuff, suppose you move plus around minus. So what happens? When you move plus around minus, what happens is that minus will intersect the line of the plus. So I move them not rotating. They stay these sort of things, they stay horizontal, these disease elements stay horizontal. So we intersect this line and we'll get multiplication by rho to the power -2, but also plus will cross the line of minus. And this will be another -2. So each of them will cross the line of the other, so it will be rho to the power -4. Now, let's suppose we have 2 points, u and v, and knowing that, we want to sort of write how f of u and v, well, given boundary conditions, would look like. Now, one thing is that you can assume that there is a model domain to which you map phi. And, well, a good conjecture that this, since you multiply by rho, and let's write that rho is e to the power 2 pi I sigma, so it's basically the same situation as for Ising, and this is e to the power -2 pi I sigma, minus 4 pi I sigma. So this is basically this basically means that it is e to the power sigma form, so it means that you would put here phi prime of u to the power sigma. Here it would mean that you would put phi prime of v to the power sigma. And here one goes around another. It means that you would put phi of u minus phi of v to the power twice sigma. And you have a monodromy. So for example, the most hilarious thing that if you have Ising type models which are fermions, sigma is 1/2, so you put here phi of u minus phi of v to the power 1, and then there is no monodromy. It's exactly the last thing. So sigma 1/2, no monodromy. But otherwise it's a fractional power, so there is a monodromy. And then the very interesting thing, so let me just write the last formula. So if you send v to u and you ask where this thing converges. So it's an easy calculation. So it will converge, so it's say v is equal u plus epsilon. So you normalize epsilon out. So what will happen is that you will get 1 over epsilon to the power 2 sigma 1. And then it turns out that normally you would expect gradient of our thing, so we would expect something like that. Yeah, Nikita, yeah. I always knew that you're a smart guy, you knew what is P, and I now repeated your joke. But here there are trivial boundary conditions. We cannot have a non-trivial gradient of Gaussian free field in a disk with 1 point. So when they collapse, you only have the next term, so you have epsilon squared over 6 Schwarzschild of phi. And wait a second, epsilon square, there should be sigma here, to the power sigma you have. Yes, and well, basically, yeah, okay. So let's say epsilon square sigma, and sigma over 6 obviously is equal to C over 12, where C is the center of charge C and not the other one. Okay, so that's the bottom line. I can say 3 morals, but Pasha is looking at me. He wants coffee. Or I can say 3 morals short. What do you want? I am actually exactly, I started at 08. 4 more minutes. Wow, jackpot today. Thank you, Pasha. I love you even more. Maybe even more than Nikita. Yeah, that's, no, don't listen to that. Yeah, okay. So what are the morals? So the first moral is sort of that covariance is equivalent to boundary value problem. That's sort of, and the same object, you can start with the same Gaussian free field in a disk, but when you map it elsewhere, impose different covariances, you get very different one. So basically what we get here is that for different values of central charge, we have Gaussian free field, which satisfies this formula where alpha is a function of central charge. And we already have seen this for random surfaces in the work of Scott Sheffield. But I tried, well, sort of, I saw it before in this classical thing and without randomness, without quantum gravity, and tried to find it. Now I found it. Now the second thing is that monodromies are really a great thing. They really can differentiate. So it's basically Green's function for d bar, but with monodromy. And I've never seen it before in potential theory. I asked Carlson whom should I talk to. He said Calderon or Alforce. I said they both of them are dead. I said, well, he said you are out of luck. So it's, but really it was a classical thing which people discussed in 36s, but you can find it in some obscure papers, but it seems very interesting. Now, the other thing, how do we get here the gradient of Gaussian free field to stress energy tensor? We've used 2 parafermions. Now, we did this already in Ising for the energy field with Clermont-Mongler, where we rigorously wrote the energy field, and we wrote constant before, which wasn't known to physics people. But there it was clear. You fuse 2 fermions, 1/2 plus 1/2 is equal to 1, so you get a boson, you get gradient of Gaussian free field, everyone's happily dancing around. But here we fuse 2 parafermions of spin sigma, but we still get a boson. Why? Because this monodromy, it actually kind of, you can reformulate, you can assume sort of non-rigorous, that it's not monodromy, but you work on a cone. So the angles of these cones, they actually make fermions out of parafermions, sort of. So this is this, whatever, background charges, if you wish. But in complex analysis, it's really that you have 2 parafermions. Parafermions in complex analysis is a dz to the power sigma form. You fuse them with monodromy, and this monodromy makes a boson out of them. So it's kind of a, yeah, I don't know, bosonization. As far as I know, I haven't seen it in physics. And as I said, with John, we spent twice a week trying to dig this up and couldn't. But we are now wiser, I hope. You're bored. No? That's it, yeah, for today. Wow, I had enough questions during the talk. Or you're allowed to ask, yeah. Yes. Why you have Schwarzen derivative? Well, it's sort of easy calculation. I was very happy to get it. Only I got sigma over 6, and I know that sigma for Ising is 1/2. but I should get 1 over 24. I was getting 1 over 12, but then I realized that sigma is different for my representation of Ising. So what basically you do, it's, well, whatever people call operator product expansion. So it's fairly easy in this case, because what you do, you write that, let's say v tends to u, so we have phi prime of u to the power sigma. Now here, if you write that v is u plus epsilon, then this thing will be phi prime of u plus epsilon phi prime prime of u plus epsilon square over 2 phi prime 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 of u plus more order terms to the power sigma. And in the denominator, you subtract phi of u minus phi of v. So what you get, the first term will cancel out, and you get epsilon phi prime plus epsilon squared over 2 phi prime prime plus epsilon cube over 6 phi prime prime prime. So this is just Taylor expansions. Now, how do you get Schwarzen from that? Well, you observe immediately that you should pull phi prime out of these things. And if you pull phi prime out, it will cancel out with these two phi primes. This one will cancel out because of the powers. So what you will get a thing of the sort and you pull epsilon to the power 2 sigma, so already we are halfway there. So the upstairs you get 1 plus epsilon phi prime prime over phi prime plus epsilon square over 2 phi triple prime over phi prime. And downstairs we get 1 plus epsilon over 2 phi prime prime over phi prime plus epsilon squared over 6 phi triple prime over phi prime. As Peter Lux said, never differentiate in public. But you see, and you should take this to the square and then everything to power sigma. And then this is easy to calculate. So it's clear that everything, it will be either you have the term epsilon which can only contain this, and it cancels out. And then epsilon square will contain combinations of these two. And there is a litmus paper which tells you whether you got it wrong or not. You got it correct if you got the Schwarzen, if you get the correct relations of coefficients. So it's usually the first time you don't get correct relations of coefficients. Well, Peter Lux just said never differentiate in public, but also it's very hard to differentiate alone.
May? No.
You know what I will suggest?
I have a suggestion.
I can just one quote. So in Notices of IMS, there is this kind of basic notion series of papers. What is something? There is a paper, what is Schwarzen? And it explains for other instances where Schwarzen logically pops out. Not this one, but indeed Schwarzen is a very nice thing. So it's...
Okay. I have an organizational announcement and a suggestion. And suggestion is to follow the advice of the Peter Lux and the speaker and let public go and get some coffee. And if people have more questions, Stas is around.